Hi, I am Avinash Paliwal, a PhD student at Texas A&M University in the Aggie graphics group, and today I'm going to present some of my recent research on sparse novel view synthesis. Novel view synthesis is the process of synthesizing unseen images of a scene from novel cameras based on a set of given images. It is a popular research area with a lot of practical applications, such as the immersive view feature of Google Maps, which allows you to navigate in 3D, generating insights for automotive companies based on 3D inspection from 2D images, shopping in augmented reality by placing objects in your surroundings, VR telepresence, which allows you to communicate using 3D avatars, and light field 3D displays, to name a few. To utilize novel view synthesis for such practical applications, the view synthesis algorithm should satisfy certain criteria. The algorithm should work with sparse input images because most existing applications utilize a sparse camera setup, and most existing media is captured as a collection of sparse images. For example, most people capture a scene by taking a quick snapshot from their camera, and majority of the smartphones nowadays come equipped with a dual camera setup. So an algorithm tailored for stereo images can be immensely beneficial. And finally, in a general setting, we might have a collection of arbitrary posed images. Sorry. And finally, in a general setting, we might have a collection of arbitrary posed images available for novel view synthesis. Therefore, for practicality, it would be logical to target novel view synthesis algorithms for such sparse camera settings. In addition to tailoring for sparse input settings, the novel view synthesis algorithms should generate high quality results with realistic effects, such as the moving highlights in these examples. Finally, the algorithm should have fast inference to enable a lag-free experience. While there are existing algorithms that work with sparse inputs, most of them either have slow inference or generate results with significant artifacts. Therefore, our goal is to introduce a set of approaches that generate high-quality novel views with fast inference. We will start by tackling the single image setting, followed by arbitrary posed images, and then briefly discuss some of our future work. Let's start with the single image algorithm. Here I'm going to introduce Reshader, a novel approach that provides realistic view-dependent highlights for this task of single image view synthesis. This work was done in collaboration between Texas A&M University and Leia Inc. and was presented at SIGGRAPH Asia 2023. Our goal is to synthesize novel views from a single input image with a focus on view-dependent effects. Here the highlights move on top of the hardwood floor in a way that improves the photorealism of synthesized novel views. Many recent works have attempted to tackle the problem of single image novel view synthesis. In the discussion, we categorize these works into two classes, modular and end-to-end. Let us first take a look at the modular approaches. Modular approaches break down the problem into smaller tasks and address each one independently. For example, 3D moments, a modular approach uses an input image and monocular depth obtained from a pre-trained model. The image and depth are separated into multiple layers based on the depth to create a layered depth image representation, or LDI. The holes in the representation are filled using an in-painting network, and this representation can then be finally used to render novel views. All the stages like depth estimation and in-painting in these approaches are trained independently. These approaches can synthesize high-quality novel views for a diverse set of input images. However, they do not generate any view-dependent highlights, making the highlights appear stuck to the surface. This is due to the implicit assumption that of these approaches that all the surfaces are made up of purely diffuse materials. In contrast to the modular approach, here the entire system is trained end-to-end by relying on various representations like MPI or NERF. For example, in one of the approaches, given an input image, an end-to-end trained model directly predicts an MPI representation. This representation can then be directly used to render novel views. The advantage here is that this approach has a relatively straightforward training process compared to the modular approaches. Plus, it can potentially encode and generate view-dependent highlights using the powerful representations. However, despite the capacity to produce view-dependent highlights, these approaches struggle to generate them for real input images. To understand the source of the problem, let us take a closer look at the end-to-end training with an example. Here, the system generates a novel view based on the input. Next, the error between the ground truth and the output novel views are minimized. Now let's focus on the two highlighted regions in the input and the ground truth novel view image. In the green inset, we can see that the background has shifted significantly between the input and novel view. In contrast, view-dependent highlights don't often alter the image feature significantly, thereby creating similar looking regions as shown here. Therefore, this system mainly focuses on fixing the misalignment problem, as the contribution due to the shading differences is not significant. To address this issue, we take a closer look at the image formation process to understand the relationship between the input and novel views. Let's focus on this point on the table marked in red. Light from a light source bounces off of this point and projects to a particular pixel in the input view. Similarly, we get a projection of this point in the novel view. Basically, these two pixels in the input and novel view correspond to the same point in the scene. When we measure the displacement of these pixels from the left image edge, as shown by the blue arrow, we can see that they don't match. So the first task is to move the pixels in the input image such that they align with the novel view. We call this process pixel relocation, and this is the fundamental challenge that all existing approaches tackle. However, the position is not the only difference between the two pixels. As we zoom into the pixels, we can see that the pixels also have different shading. The shading of the input pixel is based on the outgoing direction towards the input camera. Similarly, for the other pixel, it is based on the outgoing direction towards the novel camera. Therefore, during novel view synthesis, we also have to change the shading of the pixel. We call this pixel reshading. Based on this observation, we propose to break down the process into two independent stages: pixel reshading and pixel relocation. Specifically, our reshader takes the input image along with the monocular depth as input. In addition, we provide the novel camera pose as input. The reshader outputs a reshaded image based on the novel camera pose. We then pass the reshaded image along with the monocular depth from the previous step and novel camera pose to a pixel relocator. The relocator moves the reshaded pixels to the correct view-dependent position and produces the final novel view with realistic view-dependent effects. For our approach, we train the reshader network while relying on an existing pre-trained relocation model. To better understand the process, let us take a closer look at the outputs of each stage. The blue cameras represent the input view, while the red ones represent the novel view. For the reshader output, we get moving highlights based on the novel camera position. However, the texture of the scene remains static as it depends on the input camera. The relocator moves the reshaded output to the correct pixel positions, thereby creating texture and highlights based on novel view. Next, we will focus on the reshader model. You can find out more details about the relocator in the paper. Now, let us take a closer look at the reshader training process. We train a unit that takes the RGBD image as input. The camera pose is incorporated at the unit bottleneck, and we obtain the reshaded image as output. We augment the depth input by applying frequency encoding to every depth value, which generates a multi-channel depth input as shown here. Next, instead of directly passing the camera information to the unit, we utilize a fully connected neural network, a multi-layer perceptron, to provide learned features as input. We will show the effect of both frequency encoding and MLP in the oncoming slides. Now, to train the network, we need a dataset of input and reshaded image pairs, along with the novel camera pose. We generate this dataset synthetically using a path tracer. Consider a scene with an input camera shown in blue. We render the input image as usual using the path tracer. For the reshaded image, we place a random novel camera around the input camera. During rendering, we compute the first surface intersection points using the primary rays from the input camera. Then, we shade those pixels with the rays coming from the novel camera. As a result, the reshaded image has the same viewpoint as the input image, but shading from the novel camera's viewpoint. To highlight the difference in shading, I'm going to toggle back and forth between the input and reshaded image. Note the difference in highlight positions on the table and sofa. We create a dataset based on 9 synthetic scenes. For each scene, we randomly change the properties like material, lighting, and camera positions to create a diverse dataset. Next, we show the effect of some of the components of our approach on the output quality. Here we train a reshader model without the additional disparity input. Therefore, the network has to infer the scene depth from the RGB input image. And since we don't have the depth input, sometimes it has difficulty identifying object boundaries, which leads to smearing artifacts, as shown by the green arrow. Some objects at larger depth can also end up having incorrect amount of highlight movement, as shown by the red arrow. We only show the reshaded output video here to clearly highlight the artifacts. Since we pass disparity or inverse depth as input to the reshader, we notice that sometimes the network has difficulty handling faraway objects with small disparity values. To address this, we apply frequency encoding to the depth at every pixel and input this multi-channel depth instead to the reshader. We choose a unit model to train the reshader. The camera parameters are passed through a fully connected multi-layer perceptron to provide learn features to the unit bottleneck. Without the MLP, we notice artifacts in the reshaded output. We verify the effect of components numerically. Our approach with all the components enabled performs much better. Next, let's see some comparisons with other state-of-the-art approaches. We show comparisons against a state-of-the-art modular approach called 3D moments. As you can see, the highlights in their output appear glued to the surface. Our approach produces output with view-dependent effects and gives a pleasing result with moving highlights. If you focus on the shadow of the bottle on the table, you can see that our approach respects the shadow boundary and does not leak the highlights into it. You can also see that the underlying texture is preserved while our reshader moves the highlights. Here we show another example. If you focus on the car, you can see that our approach properly moves the highlights on both the window and the body. Our approach respects the geometric boundaries during reshading. That is, when the surface normal changes drastically, as on the body of the car, our highlights remain inside the continuous region. In this example, the metal parts of the fountain are shiny. Our approach moves the highlights to produce a much more pleasing and realistic view-dependent output. Here we show some numerical comparisons for the output of the reshader model. We generate the results on 3 synthetic scenes. The name input in the method column corresponds to the metrics directly computed between the input and ground truth reshaded image. As you can see, reshaded images are closer to the ground truth, demonstrating that our reshader network is properly moving the highlights in the input image. Here we show some numerical comparisons for the final output of our system. SVMPI is an end-to-end approach that does not perform well compared to the state-of-the-art modular approaches. 3D photo is a state-of-the-art modular approach. We insert reshading into the pipeline and denote this as 3D photo plus hours. The PSR improves significantly with the addition of reshading. SSM and LBIPs don't show any notable differences, since these metrics are sensitive to texture than the smooth highlights. We also compare against another modular approach, 3D moments, and the reshading again improves the PSR. We get similar improvements on the other scenes. You can find those in the paper. Here we show the reshading output for some example input image. While we can produce photorealistic moving highlights, this is a challenging task and our approach has some limitations. First, when we have highly specular surfaces like mirror, to our reshader, this appears like a normal textured surface, like a painting on the wall. Therefore, the reshader does not handle highlights for such surfaces. Next, in cases where the light sources are very close to the diffuse surfaces, like the wall here, we get strong saturated regions. The reshading network sometimes interprets the material as shiny and moves the highlights between different views. The correct result in this region would have been a static output with no moving highlights. So this was our single image view synthesis algorithm. Next, we will take a look at the arbitrary posed images problem. Now we move on to our ECCV paper, CoherentGS, Sparse Novel View Synthesis with 3D Gaussian Splatting. This work was done in collaboration between Texas A&M University, Meta Reality Labs, and LMU Munich. The goal of this project is to perform novel view synthesis from a sparse set of post-input images. To this end, we first have to choose an appropriate 3D representation. NURF is a popular volumetric representation which relies on a neural network to encode the color and density of the scene. However, the neural network is slow to train and takes a long time to render novel views. 3D Gaussian splatting is a more recent approach that addresses the shortcomings of NURF using an explicit 3D representation based on 3D Gaussians. This representation enables fast training and real-time rendering. While 3D Gaussian splatting is capable of high-quality real-time rendering, it requires a large number of post-training images. However, the optimization easily overfits when the training views become extremely sparse, for example, 3 images. Our goal is to adapt 3D.js to the extremely sparse input setting and enable high-quality real-time novel view synthesis. Previously, sparse novel view synthesis methods, such as the various NURF-based approaches, relied on regularizations like total variation loss. But these constraints are still insufficient in the extremely sparse input setting, as shown. In addition, these regularizations rely on the continuous function encoding property of the neural network. Essentially, when a point in the encoding space is altered, it also affects the neighboring regions. On the other hand, 3D.js uses a set of unstructured Gaussians to represent the scene. When a particular Gaussian is moved during the optimization, unlike NURF, the neighboring Gaussians are unaffected. Therefore, NURF regularizations are not as effective for 3D.js. To enable effective application of regularizations to 3D.js, our objective is to add coherency to the unstructured representation so that any Gaussian movement also affects the neighboring Gaussians. Before I discuss our approach, I'd like to note that there are concurrent approaches, such as DN Gaussian and FSGS, that address the same problem. They utilize regularizations similar to NURF-based approaches, for example, a monoclear depth-based correlation loss. However, in the absence of coherency, the novel views often contain artifacts, such as disconnected Gaussians on the surface. These approaches also hallucinate low-quality texture in occluded regions. Our proposed solution addresses the core problem of coherency. Now, directly enforcing coherency in the 3D representation is a challenging task. Instead, to circumvent this problem, we propose to add coherency in the 2D domain. To this end, we need an approach that allows us to control the 3D representation using a 2D function. Our solution is to assign a single Gaussian for every pixel in the input images. Additionally, the Gaussians are constrained to only move along the camera ray. Given this constraint, we can control the position of Gaussians in 2D using a scalar depth at each pixel. With this setup, we can now apply regularizations in 2D space. Note that even with this representation, the Gaussians can still move independent of each other. We need additional constraints to enforce coherency. To this end, we rely on 2 types of constraints, single view and multi-view constraints. We will start with the single view constraints. As we saw before with the current constraints, every Gaussian is free to move independently along the camera ray. Instead of directly optimizing per pixel depth, we optimize an implicit convolutional decoder that maps the scalar camera index to the depth. The series of upsampling and convolutional layers ensure that the neighboring depth values are correlated. This correlated depth moves the Gaussians together as a group in a coherent manner. Since this constraint is applied to each view independently, though, there is no coherency between Gaussians from different views. To address this, we utilize multi-view constraints that affect the entire scene representation. For multi-view constraints, we first obtain the scene depth from each view based on all the Gaussians. Then we apply a total variation regularization to smooth out the scene depth. This combination of single and multi-view constraints gives us a set of globally consistent and coherent 3D Gaussians. You can find additional details about the algorithm in our paper. Next, I'm going to show a quick visualization of our training process. The Gaussians are initialized using monocular depth, and therefore the surfaces from different views are not perfectly aligned. Our coherent optimization moves Gaussians on the surface collectively and quickly aligns them to obtain high-quality texture and overall geometry. The added advantage of coherently moving all the pixel-assigned Gaussians is that we do not hallucinate any texture in occluded regions. This allows us to perform 3D in-painting with state-of-the-art 2D in-painting models. As shown, we are able to generate high-quality novel views with realistic occluded details. Next, I will show some visual comparisons against previous approaches. We show results without in-painting to highlight the effectiveness of coherency. In the extreme setting of two input views, we generate significantly better results by aligning the surfaces from two input views. The coherency of nerve combined with regularizations is not enough in this setting. Here is another two input result from a different dataset, RGBD2. Again, our results are much more consistent. In this example, we generate high quality texture and geometry on the table without any floating artifacts on the fortress, unlike nerve-based approaches. For the future work or our current work, we are exploring the use of diffusion models. Diffusion models are trained to generate high-quality natural-looking images. Therefore, we would like to use it during the optimization to constrain the space of possible solutions from novel views to natural-looking images. Since we are short on time, I'm just going to show some of our initial results. Here we utilize diffusion models to repair and hallucinate details to generate a complete 360 scene from just 3 input images. Here is another indoor example. We also have another project where we generate complete 360 scenes from a single input image. Here, the first stage is to first estimate a complete 360 panorama from a single input image, and then predict a panorama depth, and finally some optimization to get a high quality 3D scene from a single input. Another example from a generated image. For both these projects, we plan to upload the papers to archive soon. So in conclusion, for single input image, we demonstrate the effectiveness of our reshader based on a simple unit by showing significant improvement in photorealism of novel views. For arbitrary views, we propose to add coherency to the 3D Gaussian representation, which enables high quality novel view synthesis and in-painting. For our current work, we are exploring the use of diffusion models to generate 360 scenes from extremely sparse inputs. That's the end of my talk. Thank you.
Fantastic. So we do have two questions. The first one is from George. In your well, if you want to just go ahead and take it in the Q&A.
So the question is your monocular image with the dog in the doorway example for how does your technique infer that the front edge of the rug continues straight when revealed from the novel view perspective? Does it learn that from your MLP's training data set? One second. So let me see if I get this question correct. How does your technique infer that the front edge of the rug continues straight when revealed from the novel view perspective? Continues straight from the does it learn that from the MLP's training data set? So I'm not exactly sure what the question here is, like what you're trying to ask. We essentially rely on monocular depth, and the pixels are just warped based on the depth input from the pre-trained model. So the MLP is trained along with the unit, and the MLP is only responsible for encoding the camera pose. So We do not really, I'm not sure. Yeah, I'm not sure exactly what this question is about. Oh, it disappeared. So the depth does tell you like which objects are in front, which objects are closer to the camera, and based on how close that object, the surface is, you compute how much the highlight should move. It also has to identify which regions are highlight and which regions are just pure texture. So the depth, molecular depth helps the model learn how much the highlight should move and which objects should move more. Okay, I guess you are asking about the rug here that was hidden behind the doorway. I see. In front of the edge continues and revealed from an old perspective. So I think it's more like it uses an in-painting model. This is based on the modular approach from 3D moments or LDI. So the layer depth image approach, what it does, it was right at the, let me see if I can go to the, it's far back. So yeah, right here. So when you give an input image and monocular depth, you get a bunch of layers like this, where you have a foreground layer, background, and intermediate layers, and you also have the depth. So the layer depth image approach, the modular approach, it applies in painting to the background layers behind the foreground. So you can see I have a visualization here, something like this. And the rug that you see behind the doorway is based on this in-painted texture from an in-painting network. And this is based on the training. Yeah, they train a model based on images and depth to learn texture as well as depth for hallucinated texture. So, okay, moving on to the next question. Can you give us a sense of how much computation time is required for which, I'm not sure for which paper this question is about. For this project to train a reshader model, I think it takes maybe a day or two. And for CoherentGS paper, it's an optimization algorithm, so it takes like 10 minutes to 20 minutes on a sparse input scene. Can you share a link to the 3D 360 depth paper you mentioned? 360 depth paper. Is it the results that I showed at the end? For those, we are working on the paper right now, and we plan to upload it soon to archive. It's not online yet, but it will be published, uploaded to archive very soon. Do you use pyramids for depth resolution? We don't use any image pyramids for image pyramids for depth resolution right now. Is the depth derived from a neural network? Depth guessing. So the depth for both CoherentGS and the reshader paper, we use a pre-trained model like depth anything or Midas to basically predict monocular depth for a single input image.